Hi, we are taking a look at Chapter 10, Section 3. We're looking at the area of a regular polygon. If you recall from previous chapters, a regular polygon has all sides equal and all angles equal. If you take a look here, first thing we're going to look at is the idea that every regular polygon can be inscribed in a circle. And if you also recall, inscribed means that the vertices of the polygon lie on the circle. So because there is a circle that's related to the polygons, we are going to be able to use some of the same vocabulary with the circles that we can use with polygons. So what I'd like for you to do at this point is stop the video. I want you to take at least 5 minutes to read through pages 1, 2, 3, and 4, and then come back, restart the video once you have an idea of what's going on. No, really, stop the video, take us just a couple minutes and read through it just so you have an idea of where we're going. Okay, you're back, I'm guessing, and we're going to start off talking about, of course, we have the center of a circle, but we're also going to have the center of a polygon. And the center of the polygon is going to be the center of the circle that can be circumscribed about the polygon. So in each of these pictures, point K is both the center of the circumscribed circle and also the center of the polygon. Circles can have radii. Circles have infinite radii, but we're only going to be concerned with the radii that go out to the vertices. So the radius of a polygon will be the segment connecting the vertex to the center of the circle. So if you take a look here, we're going to go ahead and connect together. There is a radius, and in each of these polygons here, a radius has been drawn. Again, the important radii are going to be the ones that go to the vertex. Other radii of the circle that we would draw would not stop on the polygon. They'd keep going, and again, not going to be as important to us. Okay, the next vocabulary word is for central angle in a regular polygon. Sorry, this should have been on the second page. A central angle is formed by two radii drawn to consecutive vertices. This is going to form an isosceles triangle in your regular polygon. So, if your polygon has n sides, it'll have n congruent isosceles triangles. A regular hexagon, 6 sides, and therefore 6 congruent isosceles triangles. Okay, we're going to go ahead and switch over to page 2 where this idea of the central angle continues. You can see in these pictures we have a central angle happening here, JKQ. We have a central angle here, SKR. And then we have many central angles drawn here on our what is that, an octagon. So what you need to know is each of those central angles that are important to me, they are vertex angles of that isosceles triangle. In fact, let's go ahead and mark that each of these is an isosceles triangle. And that's important to us because we know with isosceles triangles, I can drop altitudes that will bisect this vertex angle, etc. So if you'll take a look, in this first picture, there were 5 sides. So each of our central angles is going to be found by doing 360 divided by 5, which will be 72 degrees. In the second picture, it's a hexagon. So the central angle is 360 divided by 6, which is 60 degrees. And in the third octagon, 360 divided by 8 is 45 degrees. So each of these central angles is 45 degrees. You'll also notice in this last picture I've drawn for you the 8 congruent isosceles triangles that can be made inside of the regular octagon. Now, there is another way to get the angles of this triangle. If you also take a look, every time a radius comes out to a vertex on the polygon, it's going to bisect the angle of the polygon. So, if you remember from previous chapters, each of the angles in your polygon will be found by n minus 2 times 180 divided by n, and that's going to be each interior angle. So if we plug in, say 6 here and divide by 6, we would find out that each of our angles will turn out to be 120 degrees inside of our hexagon. Okay, so that's for a hexagon. So what happens then is the vertex or the radius comes out, it's going to bisect that 120 degree angle, and then of course you end up with 60 and 60. So in the hexagon, not only is this isosceles, it's equilateral. It's a little tiny 60. Okay, something to keep in mind, another way to get the angles in the triangles besides the whole idea of the vertex angle and then the base angles, of course, being congruent. Okay, so we're going to move on to page 3 and a little bit more vocabulary. Okay, on page 3 we have a fancy word called an apothem. Apothem, depends on what pronunciation you use. The apothem is going to be a perpendicular distance from the center of the polygon to the side of the polygon, and the apothem bisects the vertex angle of the isosceles triangle, and it's also an altitude for the isosceles triangle. I'm going to go ahead, and they seem to have been printed very light, so go ahead and put in those dotted lines so that you can see them and see that lovely apothem drawn in. Okay, so again, apothem is just going to be basically altitude of isosceles triangle in regular polygon. Okay, so that's a nice way to look at it. Now what happens then is, if I'm looking for the area of a regular polygon, then the formula I'm going to use is this guy right here. Let's go ahead and outline him in red, or a highlighter, which may be more convenient. I just didn't have one handy. So that's my important formula. Area equals half apothem times perimeter. So it's based upon the fact that, and this is something to think about, again, I'm not going to have you prove this, but you should think about what's happening. What happens is, if I have a regular polygon with n sides, if I take the area of one triangle and multiply it by n, I'd have the area of the entire polygon. Logical, because each of these isosceles triangles is congruent to the one right next to it. Okay, so then if each of my triangles has, or my polygons rather, has side S, if we take a look back up here, if each of the polygons has side S and height A, then if I do a little rearranging of all of these variables, I end up with N and S grouped together, and if I take the number of sides times the length of each sides, that actually just becomes the perimeter of your polygon. And so if you substitute in P for NS, you end up with your formula of half apothem perimeter. What that also tells us is I can find the area area can also be found by just finding area of one triangle and multiplying it by number of triangles. Okay, so that's something to think about as you're approaching the problem. Maybe you won't like the formula, maybe you'll like this method better. Okay, we're going to move on to page 4 and a couple of vocabulary questions. Okay, on page 4 we find some examples where we're just, again, marking up the vocabulary. It's asking you to make the center of your polygon black, make 2 radii red, and make the apothem green. Okay, so I'd like for you to, and then you're going to find the measures of the angle. So I'd like for you to take a second, stop the video, and in the first picture, see if you can mark or at least know which of the pieces are going to apply to these vocabulary words. Okay, here we go. Okay, so hopefully you can see a little bit better than I can that I've outlined these 2 radii because those are the ones that mark one of the isosceles triangles in this square. And then, of course, your center is black, and then this piece right here in green is your apothem. I'm going to switch greens for the next 2 pictures because this one kind of blends with the black from my view. So let's go ahead and, again, find the different angles. So take a second, stop the video, see if you can find them, and then we'll talk about them in a second. Okay, here are the values for angle 1, 2, and 3. And let's go ahead and put M's there for measure. If you take a look, again, angle 1 we find by taking 360 degrees and dividing it by 4 because there are 4 sides in this polygon. So each of the central angles will be 90. Then the apothem comes down and it bisects the central angle, so that 90-degree angle gets cut in half and becomes 45 degrees. And then, of course, this little right triangle, if it has one 45-degree angle, the other one must be the complement of that, which would, of course, also be 45 degrees. You can also consider the fact that the radius bisects the interior angle, and of course this was 90 for a square, and half of 90 is 45. Okay, in the second picture, again, go ahead, stop the video, mark the appropriate values, and let's go ahead and see if you can find your angle measures too while you're at it. Okay. Oh, that's a much better green. You can actually distinguish it. So again, I've outlined that central angle, which turns out to be 60 degrees for angle 1. Angle 2 is half of that. And then angle 3 is going to be the complement to angle 2 and also half of the interior angle of a regular hexagon. Okay, take a second and see what you get for C. Okay. This last figure is a dodecagon. It has 12 sides. So we can see angle 1, the central angle, turns out to be 30. We can see that angle 2 will be half of that, which is 15. And then, of course, angle 3 will be the complement of that, which is 75. Also take note, what that tells me is the angles, interior angles of a dodecagon are all 150 degrees. So that's the end of this video. We will work on the rest of the examples in class because this is kind of a tough section. So stay classy.